Hello learners, this is Habeeba with Excelwithme. If you like the video, please do like, share, subscribe and comment below. Let's start today's class, that is correlation of techniques from research methodology. The subtopic is regression analysis. Quickly do this because it's a long topic. We will just go through with the main points. In regression analysis, let's understand the concept. We have two types of variables. One is dependent or explained variable and the second one is independent or explanatory variable. As the name explained and explanatory suggests, the dependent variable is explained by the independent variable. Now, regression analysis is one of the most commonly used statistical techniques in social, behavioral, and physical sciences. Its main objective is to explore the relationship between a dependent variable, alternatively called criterion variable, and one or more independent variables, alternatively called predictor or explanatory variables. Very important, we have to remember the terms. In the simplest case of regression analysis, there is one dependent variable and one independent variable. When we take one very simple topic, for example, if I want to see the impact of emotional intelligence on academic achievement, I am taking only one dependent and one independent variable. Now, usually we denote the dependent variables as y and independent variable as x. Suppose we took up a household survey and collected n pairs of observations in x and y. The next step is to find out the nature of relationship between x and y. The relationship between x and y can take many forms. The general practice is to express the relationship in terms of some mathematical equation. Now, the simplest of these equations is the linear equation. This means that the relationship between x and y is in the form of a straight line and is termed linear regression. When the equation represents curves, not a straight line, the regression is called non-linear or curvilinear, we call. A large number of problems can be solved by linear regression and even more by means of transformation of the original variables that result in linear relationships among the transformed variables. It is assumed that the predicted values from multiple regression are linear combinations of the predictor variable. That means a large number of questions or the problems solved through this linear. If it is a straight curve line, then that is linear. If it has a curve, then it will become the non-linear. And if more by means of transformation of the original variables, which results in the linear relationships among the transformed variables. Therefore, the general form of a prediction equation from multiple regression is as follows. You can see here y equal to whatever variables we are taking. Please note down this formula where y is criterion variable, x is predictor variable. Intercept. What is intercept? The predicted value of y when all the predictors are 0. The intercept A is so called because it intercepts the y-axis. It estimates the average value of y when x1 equal to 0. Now B, constant or regression coefficient, how much of a difference in y results from a 1 unit difference in x. So 1 by E, that is residual, the difference between observed y and predicted y, values of y. Now P, number of predictors. The general purpose of multiple regression is to investigate the relationship between several independent or predictive variables and a dependent variable. Now let's understand simple linear regression, multiple linear regression. First, simple linear regression, that is simple linear regression involves only two variables, one dependent variable y and one independent variable x. We have to remember y equal to a plus b x plus e. The first step in determining whether there is a relationship between two variables is to examine the graph of the observed data, that is y and x. The graph is called a scatter plot. Now, statistical packages such as SPSS, SYST, AT or Statistica can be used to draw the scatter plot. Now, if there is a relationship between the variables x and y, the dots of the scatter plot would be more or less concentrated around a curve, which may be called the curve of regression. For example, if we take the curve like this, if the scattered dots are near this curve, this is called the curve of regression. Now, in particular, the particular case when the curve is a straight line, it is called the line of regression, and the regression is said to be linear. In addition to the linearity property, the scatter plot is also useful for observing whether there are any outliers in the data and whether there are two or more clusters of points. Now, for the population, the bivariate regression model is y1 equal to 1 plus b x1 plus e1, where the subscript I refers to the ith observation, a is the intercept and b is the regression coefficient. Now, regression equation is thus a mathematical model describing the relationship between x and y, we understood. Now, in most cases, the model does not define the exact relationship between the two variables. Rather, we use it as an approximation to the exact relationship. An important question is, how close is this approximation? That is a very important question. Now, you can see your linear regression graph here, given here. You can see clearly this is the line, linear curve, and these are the dots here, data point. This is outlier. So 95%, that is confidence band. And what happens? The thing we want to explain, that is dependent variable, and then line of best fit. This is the line of best fit. If you only had data on x, this fine line provides you a best estimate of y. If the fit is strong and no major outlier, x could be used as a surrogate or forecast of y. So, here we can see 0.77, that is R square, that is correlation coefficient we are talking about of the, that is 77% of the variance in y is explained by x, that is below 30% means they are hardly connected, about 95%, that is and they are practically the same. So, this is all about the, we are talking about this x, that is independent variable, and here y dependent variable. So, the factor we think might influence the dependent variable here. Now, objectives. What are the objectives of this regression analysis? What are the objectives? They could range from simple description of data to more sophisticated hypothesis testing or prediction. Obviously, when we set hypothesis, when we use these statistical techniques to prove whether it is true or false, that's why we do this regression analysis. Note that regression equation predicts y from x. The value of y depends on the value of x. Now, description, here the objective is to find an equation that describes or summarizes the relationship between two variables. This purpose makes the fewest assumptions. The second objective is coefficient estimation. Here the objective is to confirm or reject a theoretical or hypothesized relationship between two variables x and y. Most likely there is specific interest in the magnitudes and signs of the regression coefficients a and b. Frequently this objective overlaps with other objectives. The third one is the prediction. The prime concern here is to predict the dependent variable from the value of an independent variable. For example, If we know the number of publications of an institution over different periods, the objective could be to predict the number of publications in a particular year in the future. That is the prediction or assumption. However, the prediction depends upon several crucial assumptions. Hence, instead of a point estimate, that is a single value, we should compute an interval estimate, a range of values within which the predicted value would lie with a given probability. This range is called confidence interval. Now, what are the assumptions underlying regression analysis? We understood the objectives. Now, let's see the assumptions. With linear regression models, the straight line relationship between y and x, any curvilinear relationship is ignored. The expected value of the error term is 0. Now, the variance of the error term is constant for all the values of the independent variable x. This is the assumption of homoscedasticity. If these residual plots show a rectangular shape, we can assume constant variance. On the other hand, if a residual plot shows an increase or decrease wedge or bow tie shape, now non-constant variance, that is heteroscedasticity, exists and must be corrected. Now, the residuals are assumed to be correlated with one another, that is, there is no autocorrelation. This implies that the y's are also uncorrelated. This is so because the observations y1, y2, yn till ynth are a random sample. They are mutually independent and hence the error terms are also mutually independent. Now, this assumption can be violated in two ways, that is model misspecification or time series data. Now, what are these? Model misspecification: if an important independent variable is omitted or if an incorrect functional form is used, the residuals may not be independent. The solution to this dilemma is to find the proper functional form or to include proper independent variables and use multiple regression. Now, what is time series data? Whenever regression analysis is performed, one data taken over time, the residuals may be correlated. This correlation among residuals is called serial correlation. Positive serial correlation means that the residual in time period I tends to have the same sign as the residual in time period I to k, where k is the lag in time periods. On the other hand, negative serial correlation means that the residual in time period j tends to have the opposite sign as the residual in time period j and k. Now, the independent variable is uncorrelated with the error term. When hypothesis tests and confidence limits are to be used, the residuals are used to follow the normal distribution. Now, what are the estimation of parameters here? The random sample of observations can be used to estimate the parameters of the regression equation. Now, simple linear regression has two parameters, that is intercept and regression coefficient. Now, the method of least squares is used to fit a continuous dependent variable y as a linear function of a single predictor variable. The coefficients a, b are chosen such that the sum of squared errors is minimized. The estimation technique is thus called least squares or ordinary least squares, OLS. Now, given the criterion of least squares, the mean of the errors is 0 and correlation between errors and predictors is also 0. Geometrically, the least squares method finds the line which minimizes the sum of square deviations from each point in the sample to the point of the line corresponding to the x value. Now, standardized regression coefficient. What is it? It is the slope in the regression equation. If x and y are standardized, intercept a will be equal to 0 and standardized slope will be equal to the correlation coefficient between x and y. Now, what is standardized? Standardized means that for each datum, the mean is subtracted and the result divided by the standard deviation. The result is that both x and y have mean equal to 0 and standard deviation equal to 1. This is very important point we have to remember. Now, what is the fit of the regression model? The fit of the regression model can be assessed by computing the correlation between the observed y observations and predicted y values of y. Greater the correlation, better is the fit of the regression model. Now, the correlation coefficient is denoted by R. The square of the correlation coefficient, that is R square, is officially called the coefficient of determination, that is COD. Now, the coefficient of determination is a measure of the goodness of fit of the relationship between a dependent variable and an independent variable in a regression analysis. Now, statistically speaking, it is the percentage of the variation that can be explained by the regression equation, the variation explained by the regression equation divided by the total variation. Now, the coefficient of determination varies between 0 and 1. If there is 0 explained variation, that is the total variation is all unexplained. This ratio is 0. If there is 0 unexplained variation, that is the total variation is all explained, this ratio is 1. Now, every sample has some variation in it unless all the values are identical, and that's unlikely to happen. The total variation is composed of two parts, the part that can be explained by a regression equation and the part that cannot be explained by the regression equation. If the regression line passed through every point on the scatter plot exactly, it would be able to explain all the variation. The further the line is from the points, the less is able to explain. The ratio of the explained variation to the total variation is a measure of how good the regression line is. So, the sum of the squared deviations of x from y observation is called the sum of squares total, that is SST. SST can be partitioned into the sum of squares explained by regression and the sum of squares error, that is SSE. So, you can see it can be easily seen that SST equal to SSR plus SSE. You have to remember this formula. Now, which means that the sum of squares, you can understand through this. You can pause the video and understand all the things what are given. The coefficient of determination is computed as follows here: R square equal to SST minus SSE divided by SST. So, for testing the null hypothesis, that is H0 B equal to 0, it is expedient to represent the results of regression analysis in the form of an analysis of variance, that is ANOVA. I will explain this ANOVA in the next video here. Obviously, a large residual mean square indicators poor fit. If residual mean square is large, the value of F would be low and F ratio may become statistically non-significant. If F ratio is statistically significant, it implies that the null hypothesis H0, that is B equal to 0, is rejected. So, this is the ANOVA table for simple linear regression. You can pause the video and can see the table here. Note down the table, the source of variation, regression, residual and the total. Now, let's understand the multiple regression. What are the objectives here? The general purpose of multiple regression is to investigate the relationship between several independent or predictor variables. In linear, we understood that one independent, one dependent. Here, multiple itself tells you that more than one relationships here of independent and or predictor variables and a dependent variable. This relationship can be expressed by the following equation. You can note down this equation. Now, where y is the predicted score, x1 is the score on the first predictor variables, x2 is the score on the second, etc. The y-intercept is b0. Regression coefficients are analogous to the slope in simple regression. u1 are values of an unobserved error term and the unknown parameters, that is beta 1 and beta. Now, estimation of parameters, you can see here equations relating the n observations can be written as follows. You can note down, you can pause the video and can note down. Now, the parameters b0, b1 to bp can be estimated using the least squares procedure, which minimizes the sum of squares of errors. You can note down this formula also. Minimizing the sum of squares leads to a set of equations called normal equations from which the values of unknown parameters can be computed. Now geometrical representation, what is this is not that important for us here. Let's move forward. SE, standard error formula. I'll explain this standard error in the next class in detail about all this. Now fit of the regression model, just now we understood, just as in the case of one variable regression, the sum of squares in multiple regression analysis can be partitioned into the sum of squares predicted and the sum of squares error. The fit of the multiple regression model can be assessed by the coefficient of multiple determination. Coefficient of determination we understood here, multiple determination, which is a fraction that represents the proportion of total variation of y that is explained by the regression plane. Here fit of the regression model, you can see the graph here. You will understand. Pause it and please zoom and understand this fit of the regression model by the coefficient of multiple determination. So these are the sum of squares due to error, SSE formula here, and then SST. This is all about, you can pause and understand the coefficient of multiple determination. Now Statistical inferences for the model, the overall goodness of fit of the regression model, that is whether the regression model is at all helpful in predicting the values of y, can be evaluated using an F-test in the format of the analysis of variance. F-test is important here under the null hypothesis, that is the H0, beta 1 equal to beta 2 equal to n number here, beta p equal to 0, the statistic you can see here, F distribution with p and n minus 1 degrees of freedom. P, that is number of predictors or independent variable, and n is the sample size. You can pause the video and you can see the ANOVA table for multiple regression. Now F-test, this is very important. The following formula is used to test whether an R square calculated in a sample is significantly different from 0. The null hypothesis is that the population R square is 0. This is very important. F has k and n minus k minus 1 degrees of freedom. A common rule of thumb to reject the null hypothesis if probability F is greater than 0.5. So t-test, this is also a very important one. This test is used to assess the significance of individual B coefficients following the general formula for significance testing. Using standard errors of a statistic, t is computed as follows: t equal to b divided by, that is SB, that is standard deviation, we can understand here, where B is the regression coefficient, SB is the standard error, SE is the standard error of the regression coefficient. The resulting T is on n minus k minus 1 degrees of freedom, where n is the number of cases and k is the number of predictor variables. A common rule of thumb is to drop from the equation all variables not significant at the 0.05 level. Like all significant tests, the t-test assumes that error terms follow normal distribution. Now standardized regression coefficients, you can pause here. Already we understood what is standardized means. The estimated model also, you can note down the formula in detail. You can pause the video and you can understand the regression coefficients for standardized data. Now multicollinearity. In regression analysis, a fundamental assumption is that predictors, that is regressors, are not highly correlated. But when several predictors are highly correlated, this problem is called multicollinearity or collinearity. Now what is multicollinearity? Is the existence of near linear relationships among the set of independent variables. When variables are related, we say they are linearly dependent on each other because one can nicely fit a straight regression line to pass through many data points of those variables. Collinearity simply means codependence. Now detection, how we can detect the multicollinearity is there. This is a method here to determine this, to detect this multicollinearity. You can pause here, you can see the correlation matrix which can be used to detect if there are large correlationships between pairs of explanatory variables. So tolerance, variance, inflation factor you can understand here. Now correction of multilinearity, what is the solution here? A common approach to multicollinearity problem is to omit explanatory variables. For example, if x1 and x2 are highly correlated, say correlation is greater than 0.9, then the simplest approach would be to use only one of them, since one variable conveys essentially all the information in the other variable. So we come to the end of this video. I'll come up with the next class in the next video. If you like, please do like, share, subscribe and comment below. Thanks for your attention and time. Happy learning.